So today let me start meniscus part. So we are done with the excess pressure, right?
Yes, sir, we have.
So meniscus is a word which means basically the phases of moon, and every liquid surface will be slightly curved. So this curvature of the liquid surface, because of the surrounding wall, uh, we call this as meniscus. So if we have a, let's say, some wall, uh, let's say this is a wall, some wall, and near this wall we have some water or any liquid, not just water. It could be any liquid. So the water will not remain like this, or any liquid for that matter. So either this will take the form like this, or in some case it may be like this. But it is very hard for that. That the water will remain exactly flat. So flat is not the thing that we will be observing in day-to-day life. So either we say it's touching slightly above or slightly below. So this is a very regular phenomenon. If you look at the water inside a glass, if it is half filled, you can see slight curvature near the wall.
Yes,
And this curvature is not so prominent because the effect is just near the wall, but as you go or move away from the wall, things will change. Okay. Just so we will today analyze the reason behind the same, like why this exactly occurs if it occurs. So for that, we have to understand two concepts which I have explained before also, but let's take a recap. So there are two types of interaction between the molecules. Okay. So we have the adhesive force and cohesive force. So adhesive force and cohesive force are two forces, and the properties are very simple. So cohesive, co means together. So it's a force between similar molecule. And if we have a dissimilar molecule, then we say adhesive force. So and both are attractive in nature. So the force by nature are attractive. So attraction between the similar molecule is called cohesive force, and dissimilar is called adhesive force. So if we talk about the water molecules, so they can exert force on each other, and that is called the cohesive force. But any interaction which happens between the liquid molecule and the wall, we call it adhesive. And you must have come across these two words very often. Like if you buy Fevicol, and if you look carefully, it is written that it's a adhesive binder, which simply means it is adhesive, so it can bind two dissimilar things. So what you take is you may take some sort of laminate, and you put the Fevicol between the wood and the laminate, and then you stick together. So the force is between the surface and the Fevicol and the Fevicol and the laminate. So there are two separate interaction. I mean, three separate interaction, two adhesive and one cohesive, and that is how they stick together. So cohesive force and adhesive force are attractive forces. That is what we need to remember. That's it. Now coming back to the region of meniscus, we'll consider the molecule which is at the free surface, and not just free surface, it is touching the wall. So we would like to understand that what exactly goes with this particular molecule. Now all interactions are short range. It means the interaction will not go far away. So the wall next to that red dot will be creating some adhesive force. That's it. So when I say next, it means up to few micrometers above and few micrometers below. That is more than sufficient. Or you can say up to few millimeters in worst case. Micrometer is the attraction. So the whole idea is the dot is experiencing force. The dot is experiencing force because of the wall, and probably I can say the wall is present above and below both. And you can see that the force will be acting like this. So it is acting this way. So now if I say that the red dot is experiencing force from all direction on the left, what should be the direction of resultant force? Am I audible, guys? If I'm audible, do reply. So
Yes.
the all adhesive force, if I take the resultant of all adhesive force, what will be its direction? Left. So this is the resultant direction of all forces acting together. Okay, this clear?
Yes.
So we call this resultant force as adhesive force. Now, similarly, look at the red dot and the water, the liquid contact. And if you look carefully, you can see something that the liquid can only apply force from a quarter, correct?
Yes.
So that particle is a part of liquid.
Yeah, yeah. So particle is indeed a part of liquid only. So now what will be the direction of resultant of all these forces? Can you tell me?
Sir, in between.
Yeah, so this
So
will
it,
be at exactly at 45 degrees.
yes, sir.
So now having this information, and this force we are going to call as cohesive force we write as FC.
So the FC by root 2 will pull the water particle down, right?
Right, right. So now this FC force can be resolved further. So we are now in a good position to resolve this force. And let me do it separately, not to make this diagram dirty. So we have FC and we have FA, FA, FC, and this is 45. So this will have two components. One is below, or I can just do it here. That will be. This is how much? This is FC by root 2,
Yes.
and this is also FC by root 2. And let me make the wall part separately. Okay. So this is the situation. So now there is a tug of war between the F adhesive and FC by root 2. So these two forces are playing the tug of war. So one of them will be the winner. So we'll take the cases who is the winner. Okay. So let's take the first scenario. The first scenario is so I'm assuming that the F adhesive is exceeding the FC by root 2. So the wall is the winner. Now if the wall is the winner, we call the liquid as wetting liquid.
So like, so it will be bulged out.
We will see that. So if we represent the resultant force on the red dot that we had, okay, let me do once again. So if we apply the force, so the difference will be very small. So generally it's very small difference because now what we are having here is adhesive minus FC by root. And the cohesive part is slightly bigger. I can draw something a bigger vector like FC by root 2 and the resultant of the two. So that is pretty much obvious. So the resultant of these two, so this is called the resultant force. I mean, we can call it FR. So this is the resultant force. Now, what we need to understand or know is that the property of free surface. If we talk about the free surface is defined as a surface which is always perpendicular to the resultant force, or you can say a surface is said to be free if there is no tangential force. So now the liquid will try to take a new curvature near the wall, which is exactly perpendicular to this line. So the free surface near the wall will be along this line. Now you need to understand this is near the wall, not everywhere else. So at this position, the free surface will go like this, but as you go away, it will again become flat. The reason is the effect of wall will vanish. So essentially what you will get is, let me complete this line. Maybe I can put. So essentially the liquid surface will appear like this. And if this is the liquid surface, as you can see, why it is tilted upward. There are a variety of things you can calculate. So the most important part is the angle of contact, which is defined as the angle between the free surface of liquid and the wall, and it is always taken inside the water. So we don't take it outside. So this is angle. We call it angle of contact, and because it's a right angle, so this is 90 minus theta. This is again theta. And what we can also realize that this contact angle is a function of cohesive and adhesive forces. And that is why we can write here that tan theta c is equals to fc by root 2 upon f adhesive minus fc by root 2. So this turns out to be f cohesive upon root 2 times f adhesive minus f cohesive. So if this is the positive value, then the angle will be acute angle, and if it is a negative value, then the angle will be obtuse angle. Okay, so it will take, this formula will take care of everything, whether the angle is acute or obtuse. So this is how the meniscus is formed near the wall. Now, if we have a, okay, when we go to the capillary tube, which are very thin tubes, so the, you go in any direction, the wall is always near you, and that's why you can see a complete perfect curvature like this. So because it's a round tube, so wall is everywhere. So as you turn, you can see the wall, and therefore the liquid is curved from all sides, and so it looks quite curvy, you can say, in capillary tubes. But if you have just one wall and then there is nothing, so this effect is very much insignificant, because what you see is most part is flat, and then there is slight curvature near the wall. So if you put water in a glass tumbler, and you can see there is a curvature near the edge. Okay. So this is the meniscus part, and this is the angle of contact. So when the dominance is of the wall, when the adhesive force is dominant over the Fc by root 2, then the liquid will stick to the wall, and we call it a wetting liquid. So now this liquid will wet the surface. In the other case, it may become a non-wetting liquid. So like mercury and glass are non-wetting; they do not wet, because the dominance is there is cohesive dominance, not the adhesive dominance. So whether the liquid will wet or not depends on the the adhesive and cohesive force. So if you put a coating of maybe some oil on your body, and if you take a bath, then water will not sustain and will freely go down. And that is what people in the, okay, winter, they use this trick to not wet their body while they are taking the open bath in villages and in small cities. Anyway, so the idea is you have to take care of the adhesive and cohesive force, and by changing the surface, I can change the adhesive and cohesive force. So every liquid will not behave same with every other surface. So it depends on surface how it will behave. So if you look at the non-stick cookwares, and if you pour water, water will be like rolling on the surface. If it is less amount, you can see that also, because they create something called the hydrophobic layer, okay, of coating. So
Yes.
Teflon coating is used generally, which prevents the water to sustain, and therefore it prevents the further reaction. In cars or bikes, they charge extra for the Teflon coating, because in Mumbai it is very much required, because it's too much rain in Mumbai. So the coating prevents the water to sustain on the surface, And even the micro level sustenance of water will create the rusting very fast. So the coating is a must requirement for the areas where the rain is the of greater magnitude. Okay, in dry areas we don't need Teflon coating for any reason. And so we'll take the case two. So this is clear. I hope so. This is clear. So theta is, this is called angle of contact, and we are only talking about the contact angle of two surfaces. One is the liquid and the solid. Sometimes we may have to take the air surface. So this is also the angle of contact, but this is for the air. So the angle of contact, this is between the, and there are three types of, this is the also angle, like air and all, like complex things. So we will not go into this all other angles. What we need to take care is only the okay. So 1, 2, and 3. Yeah. Hmm.
Sir, I didn't understood that capillary example.
So that will come to later. Don't worry. So we have to study that part separately. So angle of contact is clear. Wetting liquid is clear. What is wetting liquid? So the
Yes,
angle
sir.
of contact is acute, which means it is wetting. So for wetting liquid, this must be acute angle. Now we can take the case 2. Maybe I can cover this part. This is good enough space for the case 2. So yeah. So same scenario. This is the red dot again. And now this time what I'm saying is that the dominance is the other way around. So now FC by root 2 is dominated over the what is it? So now we have here FC by root 2 minus F ADC, and this is FC by root. So definitely the resultant in this particular case will be like this. You can see the resultant forces come on the right side instead of left. And as I told you that the property of free surface is to always remain perpendicular to the resultant. So you can easily understand on your own by common sense. The free surface will try to be like this, and therefore uh, this is going to be a free surface, something like this. So of course it will become flat later on, but near the wall it is going to be like this. This is what you can see. So you can see that the the resultant force is like this, and the angle of contact has gone up. So this is the angle of contact theta c. So because this is more than 90, so this will be how much? This is 90 now. So this will be theta c minus 90, correct? And if that is theta c minus 90, so this will be also minus. So if you try to write the the value of tan theta c minus 90, you can see clearly that is FC. This is exactly FC by root 2 minus FA upon FC by root 2. But this is exactly called cot theta actually. So this is minus cot theta. So minus cot theta c is FC minus root 2 FA, and therefore you can see the tan theta c is going to be same answer. So no matter how you derive, you will get the similar answer because it will be plus or minus depending on the value, but formula looks same. So if I substitute the value, I'll get different answer. So you can see that if that angle of conductor is obtuse angle, so what we say this non so you might have seen that the water can roll down on the some of the tree leaves. I mean they will not stick to it because the angle of contact is obtuse and it's a non-wetting behaving as non-wetting liquid. Sorry. Okay. So I hope this part is clear to all of you.
Yes, sir.
So now after knowing this meniscus, okay, we are not taking the case 3 when the theta is exactly 90 degree, which is like flat surface. So you can just mention that if case 3, if f adhesive is equals to fc by root 2, then of course the tan theta c will be 0, theta c will be 0, and in that case liquid will have exactly flat surface, which is generally not the case. But this situation is hardly observed. So we can now discuss the pressure analysis. If we have a wall, sorry. So if we have a wall, let's say like this, and so just let me exaggerate the curvature. So now it is flat. After this is flat surface. So definitely this is the curvature, and what is given to us is this height. And because it's a curved surface, so we know there is something called a radius of curvature, right? If you remember. So every point will have radius of curvature, correct? Correct. So if you remember that, we can do always. Now, what is something which we need to remember that this part of the curvature will have liquid. It is not empty, so of course we have liquid below as well. So the moment you reach the flat part, the pressure here is exactly same as atmospheric pressure.
Hello.
And as we go away towards the wall from the flat part, the pressure will remain here PATM. And because the pressure here is same as, because at the same level we have same pressure, so this is also PATM. So as you go up, it will decrease. It means, so the pressure exactly at the near the below the surface near the dot. If I talk about this point, what will be the pressure here? Below the surface, not above the surface. Above surface is PATM. So again, with just one difference of side, the pressure will change. So on the other side it's PATM, but on the inside we have a pressure. Let's call it P. So what we can write is that P plus rho GH must be PAT if you go vertically down. So you start with pressure P and you go down by H value. So you increase the pressure by rho GH, and so you become equals to the atmospheric pressure. So what we can see clearly that this P is PATM minus rho GH. So the PATM is generally 76 centimeter of Hg, and the H is really very small if you see actually. Okay. So PATM is 76 centimeter of Hg, and what we can understand is the pressure P and the PATM having some relation, and that relation is that this flat surface, this curved surface will have some curvature. If you remember the radius of curvature concept in circular motion, I hope you remember this part. So how many of you remember the radius of curvature part? Okay, no. So let's say this is a circle. I want to know what is the radius of curvature of this circle. Am I audible, guys?
Yes.
So if you remember the excess pressure concept, that the pressure is always higher on the concave side, and you can see clearly that the concave side is the outside of the surface, right? And that is at P ATM, but the pressure inside, or you can say on the convex side, is less than P ATM by rho GH value. So what is the excess pressure here?
Rho G.
Rho GH, exactly. So the excess pressure is P ATM minus P, which is rho GH. And this must be equal to 2T by ROC. That's the definition of excess pressure. So it turns out to be that if you know the H, you can actually find the ROC, the radius of curvature. So this is like Olympiad level problem. And you may expect in JEE mains, because the old problem of Olympiads are now part of JEE mains and JEE advanced. So this is the question from roughly 100 years back. Okay. So this is a part of many Russian or international Olympiad, and it's very easy to analyze. In fact, given the H, I can find the radius of curvature. So as H tends to 0, the ROC becomes infinite.
Infinity.
And therefore, you can see the flat surface will have the infinite radius, correct? And the flat surface will have H0. So this is completely justifying the scenario, because as you vary the H, if you're here, we have different radius of curvature. If you're here, we have different radius. And if you come almost near flat surface, then the curvature becomes infinite and it will become basically flat surface. So that is what we have proved here using this concept of excess pressure. Uh, So is the pressure analysis part clear to all of you guys? So okay, let me take a quick attendance. So those who are present, raise your hand, and the rest will be removed right away.
Actually, function of that line is given, then we can also find the ROC, right?
Yeah, yeah. Atharv, D. Arshit, are you there?
Yes, sir.
Yes, sir.
Raise your hand if you are present.
Sir, I was not able to raise it, but I'm here.
Yeah, okay, no problem. I can hear you. All right. So now, after this pressure analysis, we can actually move towards the capillarity. So capillary action and capillarity. Try to understand this one. So the word capillary having the roots in the Greek word capillus, which means so when we say capillary tube, then it's a tube of very fine bore. You must have heard the name the bore well. So it's a bore means a hole actually, a fine hole. So capillary tubes are having very small radius. That is their main advantage. And right now it's not used much, but earlier the capillary tube was used for the blood testing and collection of blood from the. No, I think nowadays it is also used because the injection which they use works on the capillary action. So the body blood pressure is really high, and in fact, the moment earlier it was different. I mean, I can tell you the my experience that they used to prick the finger for blood test, and after pricking the finger, they used to put the capillary tube on the finger, and the blood used to get sucked inside the tube. And then they used to do blow the tube on a glass slab, and they used to make the slab multiple slabs of the blood, and that used to go for pathological test. That was like very long back. I'm saying about 25 to 30 years back way of doing things. Now it kept on changing over the years. So now we have a one single syringe they put, and then from that syringe, I mean, they keep on sucking the blood in different tubes. And what they use is the concept of the high pressure blood flow in the body. So now it's easy now. It's really improved by the. Okay, so let me draw the capillary tube. This is as thin as this. But if I draw like this, then I cannot analyze the, uh, I cannot illustrate what I'm going to teach. So what I'll do is, okay, so you can see that this tube will have some radius we call radius of this capillary tube, and this radius is generally in millimeters, and maybe sometime 1 millimeter, 2 millimeter. I mean, it's really very small. Generally, it is very small. So you can think that the human body is having infinite capillaries because we have pores, and which are the thinnest possible capillary. So when you sweat, then the pores gets. I mean, when you work out, then the pores gets kind of expanded, and the water leaks out. And the body does it naturally to maintain the temperature and all. So this is a natural phenomenon. So they can shrink the size of the pores or the capillary tube. So in case of human body, the R is a variable quantity, but when we manufacture, it's a constant. So we have pitchers, which are the earthen pots, which are also having the infinite capillaries, and these pores are capable of sucking the water and thereby releasing back to the atmosphere. And this phenomenon is called evaporation. And due to the process of evaporation, energy of the water inside the pitcher is sucked out, and that is how the water gets cooled. So the cooling phenomena of pitcher is again due to the capillary action plus evaporation. So also, I mean, in variety of situations, this capillary action is desirable. So the plants use the xylem, and these xylems are the basically the finest capillaries which the plants will have, and using this capillary, the water will rise from bottom to top. So depending on the size of the xylem, the height of the tree is decided. So if the water can go to greater height, then generally the length of the or height of the tree will be more actually. So near the equator, we have the least gravitational force, which leads to the greater capillary action, because as the G will decrease, the capillary action will take the water to greater and greater heights. And if I make G equals to 0, then water will keep on rising forever because it will never stop. So in a gravitational free space, if someone will ask you what is like up to what height the water can rise, the answer is infinite. Like you just give the capillary tube, it will keep on rising. So infinite length tube will have the infinite length liquid rising to till the tip of the tube. So the question is, will it fall down? The answer is no. The water will only go to the top and will stick there only. So there is nothing like fountain thing will happen. So the beauty of capillary tube is this: it pulls the liquid inside, and
So like water will get distributed inside.
pardon.
So the liquid will get like
Liquid will
so distributed till the end.
just wait. Let me explain. So, how exactly the capillary is capable of pulling the water up the tube against the gravity? So, for that we need to understand the concept of surface tension that we have already explored. So, look at this. So let me do the capillary tube. So the moment you touch the bottom of the capillary tube with some liquid, so what happens if it is a wetting liquid? So I'm taking the case of wetting liquid first. So if it is a wetting liquid, then what will happen? The liquid will rise like this.
Yes.
So the liquid will have the shape like this, but inside the capillary tube, the liquid will touch the wall from all sides. So this is a circular contact. So if you remember that we have done. Okay. So now what happens? Like if it is a circular contact, so the surface tension force will act tangentially in all directions. If you remember.
Yes, sir.
I'm not going to draw every line, so I've just done the two lines. That is sufficient. And this surface tension force acting in all directions will be equals to T into 2 pi r, correct? So if T is the surface tension, then the surface tension force is defined as surface tension multiplied by length of contact near the free surface. Okay. So surface tension force, I mean, just for the recap, surface tension force is defined as surface tension multiplied by length of contact near the free surface, right?
Yes.
So now once we have this, the surface tension force will have vertical component. So we know something called angle of contact, right? And this used to be the angle of contact, if you remember. So this angle is the angle of contact, as you can see, and therefore we can also calculate the vertical component of surface tension force. So vertical component of surface tension force is how much? P
T 2
into
pi cos theta.
cos theta of angle of contact, correct?
Yes.
Yes, sir.
Now the question is, who will balance this force? So right now it is unbalanced force, and because this force is unbalanced, so liquid will rise to balance. So once it will start rising, so it will eventually stop somewhere here. So what I'll do is, I'll just to make this more clear. So the liquid will rise up to, let's say, since this height. So now liquid has gone up to this height, maintaining the angle of contact. So because the surface is part of the liquid only, and you cannot detach the surface from the liquid, and the gravity will pull the liquid. So the liquid is pulled down by the gravity, and the surface tension is pulling the surface, and which is part of the liquid only. So that's why after rising to certain height, both will balance out each other, and
Yeah.
that is where it will stop. So this is called
So
the,
it would be mass per unit volume of water.
pardon,
Mass per unit volume when
mass per unit volume of what, like what you're trying to say. I'm not clear.
so the water it will rise.
Water will rise in the capillary, no?
Yes. When the mg will be equal to this surface tension, then it will stop.
Correct. So at equilibrium, the weight of the liquid that we have, I mean, that we have, taken the tube, this weight will be balanced by the Fy, and weight is due to the gravity on the whole liquid. Generally, tubes are so thin and H is so large that we ignore this missing part, and we think this is a cylindrical liquid. So we'll consider this as cylinder almost. So there are various things that we need to understand in terms of mathematics. So there are two things that we should be careful about. One is the radius of curvature of meniscus that we have discussed already, and other is the radius of capillary tube, and both are different. So sometimes you may get confused. What is that? What is this? So the radius of curvature is the the big circle, and the radius of capillary is the small r, as you can see. And the angle of contact is definitely one thing that you need to be careful about. This is the angle of contact, which is this angle. And what is interesting from the geometry, that if I say this angle is
Theta.
theta c, this also becomes theta c.
Theta c.
Now this is the relation that you need to be careful of, because this is what we use in various situations. So the theta c is not the direct answer. It is something that we derive from geometry. So you can look at the geometry and then you can figure out that, okay, this must be theta c. In a different situation, the angle will change. So the theta c may be here, but there it will be something different also. I will explain the various scenarios that this can happen. So there are two ways to solve the problem. One is the pressure analysis that we did in the last page. So if you remember this pressure analysis, exactly this is what we can do here also. Okay. So method one is very easy in terms of pressure, but we'll do the method two first. Let's method one, force method. So let me do this by force method. So at equilibrium, we can write, what we can write at equilibrium. We can write tell me.
T 2 pi r cos theta c is equal to mg.
But what is mg? Because the density will be given to you, not the mass. They give the h is given to us.
Rho g.
Rho g. No.
No, we have to add the weight. Mg, na? This is equals to mg. So what is m now?
Sir, rho into pi r square.
Correct.
And r we can replace by r sine theta c.
No, this is r actually given. So what is given to you is r only, na? Small r.
Okay.
Because you're dealing with the capillary radius. The radius of curvature is a different thing. That's not given to you. So, so the height, the liquid will rise up to what height? So you can see its answer is of 5 out. 2t cos theta c upon rho g r. So once you know the angle of contact, once you know the surface tension, once you know the the capillary tube radius, you can check the height, and you can clearly see that as R will decrease, the H will increase more. So on a tube of thin radius, the capillary action is really large, and all the plants will have the capillary. So they have the natural capillary. Even the human body is having the capillary, and that is essential for sending the water against the gravity. So the roots of the tree will suck the water, and the capillary will take it to the various branches, stems, leaves, and everywhere else. So this is the process how the the nutrients is mixed in water. So it's called dissolved nutrients, and that is how it is reached out to the different parts of the plant, and that is exactly how the plants grows in general fashion.
This process is called diffusion.
This is called
I'm asking that is it called diffusion?
no. This is not diffusion. Diffusion is something different. Diffusion is the process in which the difference of concentration is the region of flow.
Yes,
So
sir.
let's say we have something in high concentration at one place and low concentration at other place. Then the diffusion will be process in which the things from high to low will flow, and to maintain the, you can say, concentration difference in a way. You can think that. And diffusion is again a very essential natural phenomena, and yeah. So I'll explain in different contexts. In gases, it's very common, but diffusion also happens in semiconductors. So we have the p type and n type semiconductors, and the diffusion will create the p-n junction layer, and it leads to the formation of capacitors, and that leads to the formation of IC circuit and various other things. So diffusion happens everywhere. It's not just about the gases. It also occurs in solids also for charged particles. Generally, in solids we have the free charge carriers like holes and electrons, and they do flow because of the concentration difference, and that is also called diffusion. So you will study about diffusion current actually. Anyway, this is the force method. So this is very interesting method, okay, to solve the question. And for the solution, we consider this entire thing as almost cylindrical, which is generally the case. So the method two we can say as pressure analysis, which is very interesting. This is what I like, and you should also be good with this part more of it. So in the pressure analysis, we just take out the pressure at every point. So if I look at the surface just above the free surface, we know the pressure is P80, correct? But just below, the pressure is not the same. This is how much? It is P80m, and because it's a convex surface, this is minus 2T by R. Like it will be less by this value, right? Just
Yes.
okay. So now the just above the surface we have P80m, and if you remember the excess pressure concept, so pressure on the concave side is more than pressure on the convex side by 2T by R. So we can directly subtract the 2T by R. I can get the answer. Now when you go down till the bottom, here the pressure will rise by P80m minus 2T by R. But because you have gone down by H, so it will have extra pressure OGH. But because this is the bottom part, so the pressure at the bottom we know is again P80, which means the entire sum must be equals to P80, and therefore that is the equation. So you can say P80 minus 2T by R. So you can either go from the top to bottom, or you can go from bottom to top. It really doesn't matter. So you can go either way. So P80 minus 2T by R plus rho GH is equals to, this we cancel out. So what we are left with is H equals to 2T by rho G. Now this may look different formula as of now, but what we can also realize that this R and this R is always related to the for this case by this relation R cos theta C is R. And so when you do the pressure analysis, you need to substitute the R with the radius of capillary, and you can do this by writing R by cos theta C from the equation. This you can name it equation whatever, and you can see that both the answers are exactly the same. So there are two methods of derivation, and what I will suggest that be good with the force method for various reasons, but also be good with the pressure analysis method because that is more often employed in variety of situation. Okay, so I hope this is clear to all of you.
Yes, sir.
Yes.
So we'll talk about something called the Juryen's law.
Don't you know
I think-
the-
Yeah, so this formula itself is called, I think, Juryen's law. So what is Juryen's law?
Sir. Sir, I want to know the last page.
Tell me. You were saying something?
Yeah, sir, I want to know the last page. Yeah, sir, okay.
So the height of the rise of the liquid is 2T cos theta C upon rho gr. And what Juryen's law says that H into R is constant because everything else is constant. G, rho, T, angle of contact is constant. So in a capillary, H1 R1 is equal to H2 R. Those who are studying in the HSC board or yeah, HSC board only, let me tell you that this question is going to happen. I mean, come in the board exam. They definitely ask always every year. They without fail they ask the capillary action formula, the Juryen's law formula. So as the capillary size will decrease in radius, the height of the liquid will grow more and more, and that's obvious from this relationship. So H1 R1 is equal to H2 R2. So they may give you that okay, in a capillary tube of radius 2 mm, the rise is let's say 10 centimeter. So if I make the capillary tube of radius 1.5 mm, then what is the new rise? So you can just apply the formula and you can get the answer. I hope this is clear to all of you.
Yes,
So now having this formula, we can use this formula for calculation, and we have something called end correction. Now this part is for the experimental region. So in physics, we have two separate parts. One is called the experimental physics, and other is the, of course, theoretical physics that you are studying. You will not realize that what I am teaching is experimental or theoretical because both are mixed together. So in JEE Advanced particularly, they put more emphasis almost on the experimental part of physics. So like if I'm teaching you Searle's method, so that is experimental part, and then if I'm solving the remaining question, that is a theory part. So it is mixed in such a way that you cannot differentiate what is theoretical and what is experimental. So from the part that we are studying now, let's say we start with the surface tension, with then elasticity. These chapters are basically part of experimental physics because you perform experiment, you don't derive directly. So you perform experiment and then you see something, and then from there you derive the answer. So here we have the end correction, and in case of capillary, if the curvature becomes exactly spherical, so let's say the liquid exactly rises in this fashion. So in this case, you need not to think of angle of contact will be how much. What is the angle of contact here? So in this case, the angle of contact is exactly 0, and because it is 0, so this r and the radius of curvature is r only, and in this case, we should not analyze by the pressure method, so we should stick to the force method. And why this is so? Because force method says that the Fy equals to mg, which is more accurate always, and Fy we can write as T into 2 pi r. That's it, because the tension is acting on this direction, and mg will be exactly density into volume is mass into g. So what you can see that the 2t by rho g 2t by rho g r 2t by rho g r will be equals to h minus 2 by 3 r if you solve, and then you can see the h will be slightly more than the formula that we expect using pressure analysis. And this is exactly called the end correction. And why this end correction is interesting, that because h is a very interesting function of r, and for h max, if I differentiate dh by dr equals to 0, what I'll get is or h minimum, I think, maybe maximum. I'll check this minimum or maximum. So for h max or h min, I don't know as of now. So if I differentiate, what will get? Minus 2t by rho g r square plus 2 by 3. And if I equate to 0, I'll get something. So what will be our answer equation? Minus 2t by rho g r square 2 by 3. So 2t by rho g r square is 2 by 3. Huh? Is it? Yes.
So 2 by
So r square is how much? 3t by rho g. So r is how much? Now to understand this
Sir,
part, yes,
this R is for maximum or minimum.
yeah, that is so we have to. I mean, I think this should be for minima only.
Yes, sir, second derivative is possible.
Yeah. So second derivative, if you check, it is the second term will vanish and this term will become positive. So this is definitely going to be minima. Okay.
Huh.
So you can directly write the d2h by dr square is how much? Positive, correct?
Yes.
Just a moment. Okay. So you can see the minima condition is obtained. Now we can just write H minima. So in a capillary with zero angle of contact, we can have this relation. And this question may be asked in the next 5 to 10 years in J advance. So they haven't asked so far, but I am expecting that one fine day they will ask this question. Okay. So generally, what I teach today is asked in 10 to 12 years. J will take some more time to arrive at a question like this. So we are done with the capillary and the Jones law, which is very important part. We'll do some certain derivation, and that will be the end of surface stage. So our next topic is called uh, tapered. I don't know the right spelling is this. Tapered tube, like tapered is the right word. No. Just let me check the dictionary. I don't know tapered. Okay, TAPER.
Single R. And
TAPERET. So this is yeah, PE. So tapered basically means slightly bent actually. Okay. So generally, if you go to garment shop or maybe mall to buy jeans, they say tapered jeans. You know, so this will be quite thinner and near the bottom. And then we have the parallels like palazzo. This is tapered. This is the palazzo. You can think this way. So in case of tapered tube, so we make the tube not cylindrical, rather slightly tilted. So we'll take the two cases when the tube is tapered in this fashion. Now this tapering angle, the angle at which we taper, is going to be very small. So this angle, so this angle is alpha, let's say, and the alpha will be at angle like less than 5 degrees. So for a normal human vision, it will not look like even tilted or tapered, but it is. So for all purpose of analysis, you can consider this as uh, cylindrical and solve the question. But if you try to go by the force method, and if you try to calculate the exact weight, it will be a difficult task because it's like frustum. The liquid will rise in a frustum, which may be the frustrating thing. And the pressure analysis is a better way to get the answer. And generally, they do not mention the things in complex fashion, so they will give you the the okay angle of contact, and they will ask you the answer, and they will give you the radius near the top where the liquid has gone eventually. So if this radius is given to you as r, and this is the liquid we are touching here, and we know the meniscus will be like this, and this angle will be angle of contact. So the question is, if I complete a triangle, using the meniscus curvature radius of the capillary at that location. Or can we say this angle as theta c now? Is it correct to say?
No, sir.
No, exactly. So now that is the situation in which we have to modify the angle, and it will not be theta c, but it will be some combination of theta c and alpha. So can you guess what is this angle? It is easy, just a basic geometry. So you can find this angle.
Yes, sir.
Tell me, guys, what is the angle? That angle. Okay. So just draw a line like this. Now this is alpha. So we know, yeah, this entire angle, this angle we know is now. So earlier we were knowing this angle, right? And this is theta c plus alpha. And now this is vertical and horizontal. So now this will be theta c plus alpha. So the only difference is the excess pressure will be how much? Rho gh. The first equation you can always write. And r my bad, that is not.
Sir, 90 minus plus C plus alpha.
That is, yeah, this is plus alpha.
Yes, sir.
So anyway, what you can write here is that 2T by R is, always write this question, excess pressure is rho gh. And then R we can write as R upon cos theta c plus alpha. And therefore the H becomes 2T cos theta c plus alpha by rho g small r. This is what we have. So we have the formula earlier.
Sir,
So the theta c is now replaced by theta c plus alpha. That's the only difference. Okay. Is this clear?
sir, in
Yes.
that capillary thing also we did that. We took
Pardon?
theta C only, no?
Capillary angle is the angle between the wall and the free surface, not vertical. So the capillary angle is from here to here. No? This is the wall and the free surface. This angle is capillary. The angle of contact. Is this clear?
Yeah, sir. So, sir, in that also case, the upper angle will be 90 minus theta, c, no? If it is
No,
a cylinder.
no, no. This is not 90 degrees. No? This is less than 90. How you can say this angle is 90 degrees?
So,
How
no,
can
in cylindrical, sir. So, we took theta c only.
in cylindrical we don't have alpha. No? Alpha is 0. Where is alpha? Why
So
are
what
they?
is?
Okay, this one. No? Yeah, this you have to. This is mistake.
So, yeah, that only.
So you meant to say this only? Oh,
Yes, sir.
so this is a mistake. Okay, I see. I have done here correctly. This part. Yeah. Okay, so the same question we can write by inverting the tube. So once you invert the tube, what will happen? So once you invert the tube, the angle of contact will be like this, and this is alpha. So tell me, guys, what will be the answer for the H in this case? So what you can write?
So, h is equal to 2t cos theta c minus alpha by rho g.
Correct. So this was JEE mains question. The taper tube. So okay, nothing is left, but still we can do some more deep analysis. Now this is only for the advanced part. Maybe in mains you cannot think about this question. So let's do some more advanced thing. So we have something called energy analysis for capillarity or capillary action. Okay, what is capillary action? It is the rise or the fall of liquid inside the capillary. Okay, so I should have talked about that also. So just a moment, let me confirm that part also. So in case of capillary, if you have a capillary and if you have a liquid which is non-wetting liquid, so let's say if you have a liquid which is non-wetting, in such case, instead of rising, the liquid will dip. So it will not rise; it will dip inside the tube. Okay. And now in this case, when they may ask you that what is the liquid drop in Hammond of this? So now instead of rise, there is a fall actually. And if it is a fall, So the angle of contact will be like this. Which is obtuse. And so if this is H, if this is PATM, so what is the pressure here? It is PATM plus rho GH, right? So outside we assume as flat surface. This is a liquid everywhere. Let's not consider this part. So imagine the outside is plane. So now, which side is convex side, concave side? Sorry. So this is a PATM. So this is open, and this pressure is extra pressure, which is PATM plus 2T by R. And this PATM plus 2T by R is exactly equals to PATM plus rho GH. And so similar answer, but now this time it is fall. So what you need to remember is that pressure on the concave side is more than pressure on the convex side, and the value we can calculate for different situation. So this is how you can solve the question, and yeah, that's it. And if you calculate using the formula to be negative values, then this means it will dip inside. So if you use the formula H equals to 2T cos theta C upon rho G R, and if theta C is more than 90, we know cos theta is less than 0. Huh? So if theta C is more than 90, we know cos theta C is less than 0. It's a negative answer. So because this answer is negative, so H will dip. So if H is less than 0, then instead of rise, it will fall. It is clear?
Yes, sir.
Okay, next part. So, okay, I was talking about the energy analysis in capillary. So we'll take it for the cylindrical capillary. So we'll take the first scenario that we discussed. Uh, and we'll consider that this capital R is much bigger than small r, because if it is not, then we cannot consider it as the pressure analysis will be not accurate. So when the R is much bigger than small r, then the end correction will be almost negligible. It is almost like flat. So in that case, we have to think of the work energy curve. So if the liquid has gone up by height h, density is rho, what is the work done by gravity? So gravity work done is the conservative force. We can write gravity work done is negative of change in potential energy, because that is easy for you to calculate, and therefore you can write the final minus initial. Initial we take as 0 because there was no water, and this is as good as yeah. So the work done by gravity we can write as minus potential energy is written as mg YCA, because it's a like not a point mass, it's a
Yes.
mass. So this will be equals to h by 2, correct? So center mass is here. So if you go to height h, the center mass will go only to height h by 2. So work done by gravity turns out to how much? Minus, let's keep it mgh by 2 only, just for the understanding. I can put m equals to rho into, yeah, you have the formula. We also know that at equilibrium, Fy equals to mg, and Fy we have already calculated, if you remember, 2 pi RT into cos theta c.
Yeah.
So if you want, we can replace mg by 2t by r, so 2 pi RT cos theta c. We can also replace. So the work done by gravity we can we can add this way. Okay, anyway. So just keep this relationship handy because we want to prove something. So what is the work done by the surface tension force? Work done by Fy, the surface tension force. So work done by surface tension force will be equals to Fyh. Hmm, correct? So work done by
Yes, sir.
surface tension force is Fyh. Fy is mg. It is mgh exactly. So you can see that this much is the work done by surface tension force. This is the positive work. The negative work is mgh by 2 by gravity. So you have given mgh energy. The gravity has taken only half energy. So the question is where that half energy is gone, and the answer is that half energy has gone into the heating effect, because there is no kinetic energy. So we can say the loss is because of heat. So the what we need to remember, that this delta H is equals to mgh minus mgh by 2, and the heat produced in the process of capillary action is. So this is what we need to remember, that in every capillary rise or fall, there is some part which is wasted as heat energy, and it is almost 50%, not almost, it's 50% theoretically, which means the capillary action takes place uh, in a steady fashion because it is not accelerating. So they keep on wasting energy to maintain the speed. They do not accelerate very fast. So the motion is almost like a uniform motion generally. So this part you need to remember. And now if you want to substitute the mg into other formula, density into volume formula, you can write, and so on. So there are many ways in which you can express the answer. I'm not trying to convert all answers into complex format. Depending on the question, you can do this part. So the energy analysis, and one last topic that we have is capillary tube of insufficient length. So if you have a capillary tube which is not sufficient, let's say that the H that could have the liquid has gone is this much. It's not even. So imagine, okay, this is the capillary and this is the rise of the liquid up to height H. But now what you do is What if you bring a tube which is quite smaller than this? If the tube is still this much only, so no matter what you do, the ability of the liquid is to rise up to greater height, and what you have offering, what you are offering is much smaller than that. And the R is same. Here we have R. So what will happen in this case? If you have insufficient, then what will happen now? Will the liquid come out of the tube, or will it do something else? What will happen? Any guess?
Sir, can you repeat the question?
The question is, will the liquid come out of the tube, or will it remain inside?
So it will remain, it will not spill out. It will remain inside.
So now what we need to understand is something, this phenomena. So of course it will not go out, that's for sure. Now if you remember that when I was analyzing the cohesive and adhesive force, the wall was like this. Now if your liquid will reach the topmost point, if the red dot is here, the wall is only here, and the liquid is only here. So what is interesting here? At the edge, both force will act downward. So cohesive and adhesive both will be like this, isn't it? And this was cohesive, this is adhesive. So earlier we used to say that if F adhesive is more than Fc by root 2, then it will stick to the wall. Okay. So generally the F adhesive needs to be only more than Fc by root 2, not Fc. So generally you can say Fc is more than Fa, and that is why the horizontal component, because vertical will be downward, horizontal component will dominate towards this. So what will happen is, near the edge, the liquid will always take a shape like this. And this is what we always observe in the glass, right? So if you keep on pouring the water in the glass, it will go above the glass level, but will make some what shape like this. Have you seen this?
Yes, sir.
So it will not flow outside. So
Sir,
the
I
whole
didn't
idea
understood
is,
this.
take a glass of water, keep on pouring the water till it gets completely filled, and then see the water level outside the glass. How it looks like. Tell me.
Yeah, sir, it looks like bulged out. Yeah.
Exactly. So it is bulged out because the resultant of cohesive and adhesive force will be right and down. So net force will be like this. And below will be, this is much bigger.
FA will be greater than FC by root 2.
Yeah, FC is generally bigger than FA. FC by, see, earlier we have to make the assumption that FA is more than, so this could be anything. I mean, of course, it could be anything. But if it is equal, then it will be flat. Okay. If it is more, it will be like this, and it may below also. So whatever in the case, what I'm saying, trying to say is that in this scenario, what will change is called angle of contact. So the angle of contact will no longer be the same. So near the edge, the angle of contact that we define will not be valid. So this formula is not valid. Which formula? This formula. So the angle of contact concept will go away near the edge, and you can say rather it will modify. So it is not the same as what it used to be within the capillary. Near the edge, everything will change, and angle of contact will be a variable quantity, and that is why what they do is they do not let the liquid to flow out. Rather, they change the curvature and keep it there only. So generally, if it is more curved earlier, let's say if this is curved earlier, if it is this much curve, so it will try to reduce the curve. I mean, reduce the curvature or increase the radius. So it will be like maybe this. If this will not happen, and if it is not happen, it will be try to like this. And if nothing happens, then it will spill out. So there is a like level up to which it can do. So generally, in case of capillary, what happens? In case of capillary, this goes from below till flat level because that is sufficient. Because if it is flat, then there is no pressure difference, and that's why the liquid will be balanced. So now, if I remove the atmospheric pressure, what will happen?
So it will spill out.
Now, does gravity depends on atmospheric pressure? So if you look at the formula of capillarity, do we have dependence on atmospheric pressure?
No. Oh,
We have dependence on the gravity, not on atmospheric pressure.
yes, sir.
So that's why the confusion is because of the formula. But if you look at the force method, it is quite clear because the laws of motion is the right way to analyze the situation. So what laws of motion is saying that the surface tension vertical component is balancing the gravity, and in this formula you can see clearly the atmospheric pressure is playing no role. Okay. So if I remove the atmosphere, the answer will remain same. So the H will be same. If I remove the gravity, then things will be different. So here, if I remove the atmosphere, what will happen? If you remove the atmosphere, in that case, it will take a shape bulging outside and will balance it. Because now surface tension will act this way, below. So instead of pulling up, the surface tension will start pulling downward. So it will bulge slightly above and will be pulled. So it is if it is atmospheric pressure is present, then the maximum can go is flat. If you remove the atmospheric pressure, then it will be like other way around. In glass example, we are pouring water. It is not the rise. If you keep on pouring water, then it has to bulge and then eventually it will fall. Correct? So all are different things. Rise and fall is one different part, and the glass example is different because there you are pouring the water. So if you keep on pouring, then definitely it has to go outside, and then the bulging will change from concave to convex, and then it will try to stop. And even that will fail to stop, then it will flow. Understood? Is this clear?
Yes, sir.
So there is a question that is being asked that if the radius of curvature of this part, if I say as r, and if this part if I say as r dash, so what we can say that the h into radius of curvature is also constant, but this is not Newton's law. This is something different. Here the r is curvature, not radius of capillary, and in Newton's law, the r was radius of capillary. So this difference you must bear in your mind while solving numerical. So what happens is that in case of insufficient length, the radius of curvature will change in order to keep the liquid intact. So it will never outflow, it will remain there. So h into r. So near the edge or end, there is a manipulation or modification of curvature. So curvature within the capillary and near the edge will change, but they make sure that the h dash and r dash will be like this. So if you make h dash 0, then r dash becomes infinite, which means flat surface. So that's why I said the curvature will go from the concave to flat in case of capillary. And I hope this is clear to you guys. Is this part clear?
Yes.
So h dash is the height of
Yes.
the smaller.
Height of the insufficient. So h dash is insufficient length, less than h. So if h is within the tube, then we have r as a curvature. So if it is if it is not sufficient, if it is less than h, then liquid will rise up to the tip and then we will change the curvature and will stop. So first it will go to the tip for sure, will stop. So in case of absence of gravity, what will happen? Because there is no gravity, then what will happen? So how the surface tension will behave if there is no gravity?
Sir, it will go.
If there is no gravity, then two things will vanish. In the absence of gravity, this is complex concept. In absence of gravity, the pressure of the liquid column will vanish. So rho gh because if g is 0, no matter what is h, the atmospheric pressure will be the only pressure. Second thing is in absence of gravity, it will rise because of the surface tension and it will never stop till the tip. Because there is no one to oppose the surface tension, so it will keep on rising. Up to what height? Up to the height available. That's it. So now, in case of absence of gravity, the liquid will go till here. And at this point, the curvature will become flat. Why? Because we have atmospheric pressure here and we have also atmospheric pressure here. Because both pressure are same, that is only possible if it is flat. So in case of gravity free space, the answer will be the liquid will rise to the top and will stop. That's it. And up to what height it will go? Any height which you, make available for the liquid to rise. That's it. So even theoretically, if the tube is of infinite length, the liquid will rise to the infinite length, and near the edge it will stop. That's it. That's simple logic. So the question of gravity free space will come. Then this is the theoretical answer you need to remember. The rho gh concept is only when there is a gravity. If there is no gravity, there is no rho gh. So the question is, if we are in a elevator, in elevator we have a bucket of water, and in the bucket of water we have a fish. Three things: we have elevator, we have bucket of water, or let's say we have aquarium. In that aquarium we have a fish. If I make the elevator moving down free fall, what will happen to the fish? Will it be able to swim? Float? Yes or no?
Yes.
The answer is no. The fish cannot swim because the concept
So
of
it will
buoyancy.
float. Right?
No, it will just free fall along with the bucket. Aquarium. Nothing will happen. So the floating process will stop. The flotation is only because of gravity. It's very interesting that the gravity helps you in floating also. So at the same time, it is pulling you down, but it is the same gravity which helps you in float also. And that's something very interesting. So inside the liquid, gravity helps in floating. And do you know why it helps in floating? Any idea? Anyone guessing idea? How gravity can help in floating? That's strange, no? Counterintuitive.
Yes.
So imagine if you are trying to embark on a local train of Mumbai, okay, and you know that Mumbai locals are very crowded. So you must have seen that while you're going trying to go inside, many persons are pushed outside. So in case of gravity, if the density of liquid is more than the object, gravity will prefer pulling which object first, higher density or lower density?
Lower down.
Are you full? Gravity will pull the lower density.
So higher
It's a
density.
pull down higher.
So if you're, let's say if the water and fish are two objects, water is high density, fish is less density. Gravity will prefer water or fish?
Fish. Oh, sorry, water.
Water.
Oh, sorry, fish.
Exactly. The gravity will favor the water to go towards its center, or it will pull more of water. And in the dew phenomena, the fish is pushed upward. So in a way, it is a relative push, which is like floating. Now, if you understand this concept, it's very easy to understand the the flotation process. So when, let's say if we have object which is denser than liquid, then gravity will have preference of for that object which is more denser than the lighter, and so it will sink. So the floating and sinking is as per the gravity only, and it is very interesting that the gravity is trying to pull both of them, but the one which gets more pulled will create the buoyancy of flotation for the other. Now imagine if gravity stops pulling anything, then no matter whether it is fish or water, all will remain in the same state. So the buoyancy will never develop actually. Now this is very counterintuitive that gravity helps in floating. I mean, no one believes me. I mean, when I say this word, gravity helps in floating.
Sir,
Yeah.
so fish has high density or water?
No. They have low density. Humans are as dense as water. We are almost close to water. So humans are not denser than water. The problem is humans are slightly denser than water, and that's why you're able to swim, because that slight difference of density we balance by the applying certain force, and with that force we balance the extra difference. Okay, so we use the Newton's third law, and there are many person, especially the people who are like having big tummies, they don't sink easily, they in fact float. So it is very strange that people who have fat will be more, I mean, comfortably swim in the water than who are thin. So you can imagine the whales are, can float easily than the small fish. So size really matters, because bigger the size, bigger the buoyancy. Okay, because gravity, a large amount of water you're displacing, so gravity will try to pull all water above you than you. Understood? So you will be pushed by the water above, and if the gravity will stop pulling the water down, then no one will separate you. So yeah, it's very interesting phenomena that no one try to understand this. So I hope you have understood that how gravity helps in floating.
One question.
Yes, go ahead, tell me. Hello. So if you go to, let's say, a planet called Jupiter, will it be easier to float? Yes or no? So on a Jupiter, will it be easier to float? I think I'm not able to hear your voice.
No.
So thinking so. Once.
So see, more the gravity, easier the float of lighter object. I'm saying it's a reverse flow. So if you're lighter than liquid, you will float because gravity will prefer liquid, not you. If you're heavier than liquid, gravity will prefer you, not the liquid. So whether you will sink or float depends on density, not your size, shape, nothing. Only density matters. So anything which is denser than liquid will sink. Anything which is lighter than liquid will float. That's the only phenomena. That's the only concept of fluid mechanics that we'll study after this. So I hope this part is clear to you guys.
So that's why that aeroplane and weightless it's like,
Airplane.
so if we are in airplane and if it is free falling, then we also float.
We are also, I don't know what you're trying to say, but anyway. So I hope you have understood the concept. And in fact, the air is also like a liquid for small insects. So in a way, if you think of small creatures like dust particle, like thing, for them the air is dense enough to let them float. So what they do is they create extra push by Newton's third law by pressing the air downward, and they create sufficient force to balance their weight. So for human, we are quite denser than air, and so for us it's difficult. Birds will have the ability. So birds are also denser, but they have the ability to create enough thrust by pushing the air down to fly. And in case of even lighter objects, they not every bird is flying. They try to glide actually. So they what they do is they go down, but while going down, they go far ahead. So there are some birds which will climb the tallest of the tree and will just glide from there. Just like you fly the handmade plane, hand planes, paper planes, basically called paper planes, and they glide through the air. So most of the birds are not flying. Eventually, they glide through the air, and they do fall. To rise, what they do is they flap their wings, create the Newton's third law. They push the air down. In turn, they get the force upward. They go up, and once they rise, they again glide. So they are smart enough. They don't waste their energy all the time. So not birds are always flipping their wings all the time. No, they just go high in the air, and from there they also use the air stream. So we have also air flow in the air. I mean in the atmosphere. So they go to a certain height where they can get the advantage of the airflow. So those are migratory birds. They move in a big what you say, the group. There's a special name for it. I don't remember. And they prevent each other's gliding ability. So what they do is they create a kind of V shape, and the one which is facing the front periphery are the most energetic birds, and the rest will be gliding in the airflow. So they create the aerodynamics, exactly like a plane. So not all are working hard. So now the one who is behind will be relaxing actually. So they take the advantage of the front warriors. When they get tired, then they exchange the position, and this is how the birds travel far distance by taking turn working for some time and then giving chance to the others. And when they all are tired, eventually they will sit somewhere and then again they will do the same thing. So it's just like natural process of effort, relax, energy, go back, and then okay. So the last concept is okay, but that will be taken in the chapter of fluid mechanics, that is accelerating tubes. So yeah, I think with this we complete the uh, properties of matter. No. One thing is left is viscosity. Okay. So I think today's takeaway is gravity helps in floating. Okay. I think you would.
So one
Yep.
question.
Yes.
Sir, the fat person will displace more water because of more volume, then buoyancy force will act on him more, right?
Yeah. So if you displace more water, it means
Archimedes
that
principle.
that much water is trying to go down. So you'll get the equivalent force by the water on you upward. So we'll see that the water and the water. So it's very interesting that ah any. So the last topic is viscosity. Now there are two things that we can do. We can study viscosity after the fluid mechanics is completed at the end topic, or we can study now. Then I need to have some application of fluid, which I have to explain here. So I think that will be difficult part. So what I'll do is I'll complete the viscosity at the end of the fluid mechanics. So I think we should start the fluid mechanics, and let's complete this part. Okay. So I think next lecture I will take is fluid mechanics. It's a big chapter. It will take some time. So understanding fluid is a really challenging task. I mean, their behavior, how they behave, what they do, when they do. Okay. So after fluid mechanics, we'll go back to the wave and sound. That will be the best way to complete the class 11 syllabus. So maybe I think maximum 1 or 2 months we'll be able to finish the entire class 11 syllabus. 12th will be very easy for you guys because 12th is small compared to 11, and we should be able to finish 12th in next 5 months max, 5 to 6 months max. So I'm planning to complete the whole syllabus by August or before that. Okay.
So,
Yes.
sir, I have a doubt in page number 4.
Page number 4 of today's lecture.
Yes, sir. So I didn't understood that how 2t by ROC
How?
derivation.
ROC derivation. Okay.
2t by ROC. Yeah.
Okay. Okay. So I think I have defined the excess pressure.
Yes, sir.
So what is excess pressure? If we have any surface, this is outside, this is inside, this is in, this is out. Okay. Even if I remove this part, let's see if I remove this part. So the pressure on the concave will be always more than convex, and the difference will be always the curvature of this surface. If it is R, then the P inside minus P outside is always equals to
Px.
R. And R is the radius of the sphere. Here the R is the radius of curvature. That's it. So this is you can think this is the imaginary sphere available to us. Think this way. So this is actually not present. No, this is not present. This is the hypothetically we are assuming that okay, if what if we have a sphere there, then the relation will be like this, no? The difference is 2t by r, correct? Understood?
So please will you repeat once?
See, on a concave, you have to just identify the concave side and convex side. And this sphere is only meant for that point, the white dot. So at the white dot, if I draw a sphere or in 2 dimensional, let's say circle, then that circle is behaving as a sphere. It's, you can think this way. And what I'm saying is that the difference will be so okay. Okay, yeah. So there is a problem here. This is a valid point actually. So this is only for the spherical surface. I mean, when the wall is everywhere, here the wall is only one side. So this will be like a cylindrical curvature. And okay, my formula will change. My bad. So there is a small change in the formula which I haven't given the derivation. Here the water is touching like this. This is the liquid, right? This is not a spherical surface. So here what we have is the curvature like this only, like a circle. And the formula for excess pressure in cylindrical surface, which I haven't taught you guys. I mean, I have given the formula maybe. If you remember the Laplace equation, right?
Yes, sir.
Using the Laplace equation, this radius is r, and this radius is infinite. So Laplace says that the excess pressure is how much? T into 1 by r1 plus 1 by r2. In our case, the excess pressure will be T into 1 by r plus 1 by infinity, and the answer is only 1 by T by r. So I have to change the small part, and this will be T by r. Yeah, this is now correct. So good you raise this problem because okay, I also consider this as spherical. So rather we have to apply the excess pressure formula and from the Laplace equation, and then in Laplace cylindrical surfaces the excess pressure is not 2T by R, it is simply T by R, and that is what you can remember. Okay. Now this is clear.
Yes, sir.
All right, guys. So we'll see in the next lecture with fluid mechanics. And I think I have shared the fluid mechanics booklet. Have I?
So checking one.
If not, let me know on WhatsApp. I'll send it today. All right.